All right, so I'll do the same thing that we did. I'll record as long as you're okay with me recording it and having it posted on Moodle so that you can get to it later if you'd like. Let's see if I can pull this off here so I can start writing. All right. Any issues getting the book?
Nope.
It's my first time teaching out of this particular textbook. I've taught abstract algebra a number of times, and I'm an algebraist, so I'm pretty familiar with the material. But it's the first time I've actually taught out of this book. There's, pardon me, goodness, 3 traditional structures that are usually covered in an abstract algebra class. Groups, rings, and fields. They're typically what they're called. They sound, well, maybe ominous, but they're not really that bad. So a group is just some structure that has an operation that tells you how to combine 2 things. That's what a group is. A ring is a structure where you have 2 operations that tell you how to combine things. And then a field, I'll mention what that is here in a minute. But rings, part of a ring is a group. So a lot of books will start with groups and then do rings. This book does it the other way around. They start with rings because rings feel a little bit more familiar to you. So what we mean by a ring is that you can add, you can subtract, you can multiply, but you may not necessarily be able to divide. Okay. So what I mean by that is if you think about just integers, if I add 2 integers or subtract 2 integers or multiply 2 integers, I always get another integer. But if I take 2 integers and divide them, I may not get another integer. Okay. So that's an example of a ring. And that's one of the reasons why I believe this book starts with rings, is because it's a little bit more familiar. You're used to doing addition, subtraction, multiplication, and division, and you also should be familiar with the idea that I may not always necessarily be able to divide and get the same type of thing. Okay. A field is just a ring where you can divide everything except for 0. I can't divide by 0 in any structure. But generally speaking, I can take 2 things and divide them and still get another thing that's in that structure. So rational numbers, your fractions. If I divide fractions, I get another fraction. Real numbers, if I divide 2 real numbers, I get another real number. Complex numbers, if I divide 2 complex numbers, I get another complex number. Okay, so those would be examples of fields. Okay, so we're going to start with rings and fields, and then we'll move to groups and get a little more abstract. But before we do that, we're going to do a little bit of review of discrete types of things. All right. So I just mentioned that in rings, you want to know whether or not you can divide something. So we're going to start with reviewing what the division algorithm is. So remember your division algorithm. This is section 1.1, by the way. I can write. All right. So when we talk about dividing, think about back in grade school when you did division. You take one number, put a number into it, you do long division, you get that number at the top, and then you go through, and at the bottom you get something that may be left over, and then you put like an R in that number, right, for remainder. It's exactly what our division algorithm says. So let's let A and B be integers. And as we're going through this class, I'll use more symbolic notation that you're probably already familiar with, but just as shorthand to help write things down a little bit faster. So here I'm just using the element symbol, and then we use what we call blackboard bold for Z. Many of you are familiar with the notation anyway, but just mentioning it. Let's let A and B be integers. We'll let B, we can let B be non-zero, but just for simplicity, we'll just say that the B is greater than 0. You can still do division algorithm with negatives. It doesn't matter, but in this case, let's make it be greater than 0. What I do not want is B to be 0, because B is the thing I'm going to divide into A, and I don't want to try to divide by 0. All right. So then there exist, no, we'll write it this way. I told you I'm going to use symbols. If I use a backward E, capital E, that's a there exists. If I put an exclamation point back behind it, that's not factorial, which wouldn't make much sense. That means there exists a unique. So if you put an exclamation point behind it, it's telling us about unique. So there exist unique integers, Q and R. So lots of symbols, right? I'm just getting a string of symbols and not writing much words. Then I'm going to say such that, and if you want a little shorthand notation for such that, take your element symbol and write it in reverse. Such that. It's pretty standard. Sometimes people will emphasize that we have a such that by putting a colon behind it, but I don't do that. So if you see somebody else put a colon behind it, it still means such that. All right. So such that, what do we have? We have A is BQ plus R. So again, we're dividing the A by the B. So the Q is standing for the quotient. The R is standing for the remainder. Okay. So we're just without writing it with fractions, we're just writing it how we could do it in this particular way. I don't like to write it with fractions, generally speaking, because again, I'm talking about integers. I want everything to be in the integers. If I start writing on things with fractions, I have to make an argument why I know it's not an actual rational number that's not an integer. Okay, so that's why we're writing it this way, so that everything here is in the integers for certain. Okay. The other part that we need to make sure that everything's unique here is that our remainder, remember that when you do the remainder, of course we get non-negative remainder. If the remainder is 0, then of course B evenly went into A. But the other part we need to make sure that happens with your remainder is that you're not bigger than what you divided by. And that's how you knew when you quit in grade school, right? When you got down and the number that you had left at the bottom was smaller than what you were dividing into the bigger number, that was when you knew to quit, and that was your remainder. Okay. So same concept here. So this is what the division algorithm says, and it's useful in different applications for proofs that we'll do. I thought I marked one that I wanted to actually do. I was going through this the other night. I keep thinking I pick out problems to do, and then all of a sudden it's not in my book anymore. Anyway, let's look at number 7. And this is number 7 in the book. I'll write it down what it is. This is number 7 on page 8. So number 7 says that we want to prove that the square of any integer is of the form 3k or 3k plus 1 for some integer k. So one of the things that's pretty typical when you're working with integer types of things, and it's trying to say something is of some form of a number times another integer, it wants you to apply the division algorithm. So notice I've got either 3 evenly divided to the a, that would be the a is 3k, or when I divided the a by the k, try that again. When I divided the a by the 3, I got 1 left over. Okay. All right. So anytime that you see a problem like this, it's probably trying to direct you towards the division algorithm, and it's also probably trying to tell you that you're trying to divide by 3. Right? Okay. So let's think about it for a second. If I divide something by 3, what are your possible remainders? 2, 1, or 0, right? Those are the only possible remainders. So what's this one trying to tell you to eliminate? 2. Yeah, remainder 2, right? Okay. So let's go in here and take our a. Oops. Let's let a be an integer. Let's take a and divide it by 3 first. So by the division algorithm, what do we know? Well, the division algorithm says that if I want to divide A by something, there exists unique Q and R, where R has a certain property, right? Okay. So by the division algorithm, there exists unique Q and R that are integers such that A is equal to 3 times Q plus R, because again, we're going to divide it by 3 in this case, right? And we just said, you just told me a second ago that the only possible remainders when I divide something by 3 is I get 0, 1, or 2. Right? Okay. So that's just starting with A, right? I took A and I divided it by 3. What is it we're trying to prove something about? Not A, but the square, right? So what do you think I want to do with these 3 possibilities that we have? So either I have A is 3 times Q, A is 3 times Q plus 1, or A is 3 times Q plus 2. What do you think I want to do with those 3 possibilities? Square them. Good. All right, so let's take A squared, and in the case where we have 3Q, that's case 1, right? What do you get when I square 3Q? Yeah, you get 9Q squared. But remember, what are we trying to show that A squared, what form are we trying to show that A squared has? It needs to be 3 times something, right? So how do I need to rewrite this so that I have 3 times something? Yep, good. 3 times 3Q squared. Now again, it says that K has to be an integer. Is 3Q squared an integer? Yeah, because Q is, by squaring an integer, I still get an integer. So if I take 3 times an integer, I get an integer, right? Okay. I guess I probably, if I want to be a little bit more emphatic here, I'll say K equals the 3Q squared as an integer, just because I said K in my original stem of the problem, right? Okay. That's a case 1. What's the next case? What do you think we want to do? Yeah, 3Q plus 1. If I square 3Q plus 1, what do we get? Plus 6Q, yeah. All right. So the first question, now remember the stem of the problem says that we need 3 times an integer or 3 times an integer plus 1. Which of the 2 forms do you think we're going to use here? Yeah, 3 times an integer plus 1, right? So how do you think we should rewrite that so we see it?
Just 3 times 3 squared plus 6Q. I mean plus 2Q.
Good.
And then close brackets plus 1.
Good, yep. And what's playing the role over K? Good. I guess let me emphasize that we're calling that my K here. Last case is? Yeah, 3Q plus 2, good. Multiply that out, you get
9Q squared plus 12Q.
Wow, that is some really bad handwriting. 12Q plus 4. How do we want to rewrite that now?
3 times 3q squared plus 4q plus 1 close bracket plus 1.
Good, exactly right. Yeah, we need to be a little bit. We got to be a little bit clever with the 4, right? Pull off a 3 and then factor out the 3. The cleverness comes from the fact that, again, we probably want our remainder to be a plus 1 there because 4 is not divisible by 3 and the 9 and the 12 are. Right? So make the 4 a 3 plus 1, then you can factor out the 3. And now again, just to emphasize, our k is going to be the 3q squared plus 4q plus 1. And again, that's an integer. Oops. And those are the only 3 cases that we have, again, because our remainder we said is 0, 1, and 2. The only possibility is when we divided the a by 3. So we used those 3 cases. So at the end here, just to make a little summary statement, we can say, therefore, a squared is of the form 3k, or 3k plus 1 with k an integer for all integers a. Okay. So this is, I would say, a pretty prototypical example of how you use the division algorithm to start to write something. Okay. So notice in this case we divided it by 3, so it has to be a 3k, a 3k plus 1, or 3k plus 2. If you had a problem where you're going to divide it by a 5, then you could write it as a 5k, a 5k plus 1, all the way to a 5k plus 4. It's pretty typical if you want to break it down into cases using a division algorithm that way. We happy with that one? We'll come back to the division algorithm here and there as we go along. Also notice that one of the things the division algorithm gives you that is also helpful quite a bit is if you want to write an even number, it'll be a 2 times something. If you want to write an odd number, it'll be a 2 times something plus 1. So if you know if something's even, you know how to write it. If you know if it's odd, you know how to write it. Okay. All right. So I'm not going to go through the proof because I don't want to take the time to do it. But the division algorithm is a consequence of what we refer to as the well-ordering principle. I will mention the well-ordering principle. So the well-ordering principle is a concept about subsets of integers, in particular subsets of non-negative integers, but really you just need to make sure that you don't let yourself go off to negative infinity. So what the well-ordering principle says is that every non-empty subset of positive integers has a least element. Again, you can extend this to, you can keep going to the left on the number line, but you can't go on to the left forever. So say you want to start with -5, that's okay. So any non-empty subset of integers that go from -5 to infinity would also have the smallest element. Or if you want to go down to -1,000, the same statement, you just can't go off to the left-hand side of the number line forever. There has to be a bottom to it. So this is what's known as the well-ordering principle. You can use this to prove the division algorithm. So the way, I'm not going to go through the whole proof, but the idea would be is, let's suppose that B doesn't evenly divide A. So you would let S be the set of all A minus BX, where your A minus BX is greater than 0, then the smallest element of this set is the remainder. That's how you use it to get the remainder. It doesn't give you the uniqueness part. It gives you the existence of the Q and the R. That's how the well-ordering principle would work in this case, to give you the remainder, and then the Q that corresponds to it. One, I'll call it tricky part. It's not really particularly tricky, but notice that in the well-ordering principle, you need a non-empty subset to be able to use it. Okay. So the first thing that you would need to be able to argue before you try to apply the well-ordering principle would be that you actually have something in that set. So that would require some cases. Actually, this one's not that hard. Remember when we stated the division algorithm, we said B had to be positive, right? So make your X negative, that'll make an A plus B times something. And then if A happens to be negative, you know that you can make B times something bigger than A at some point. And so that will give you some element in there. And so then you can start talking about a non-empty subset. Again, that's a technical point, but an important one. It's kind of like when you do inductive proofs. When you do a proof by induction, you have to have that basis step. If you don't have a basis step, you can't build from the basis to go on. As a matter of fact, induction is another consequence of the well-ordering principle. All right. Anyway, I just wanted to mention it because we're going to use it in the next section here in a second when we talk about greatest common divisors. But as a side note, stuff that gets harder and stuff that we won't talk about past this second, what I'm going to talk about in the next 30 seconds. There is a, I can't remember the name of it now. Off the top of my head. There is a statement in mathematics that says that every set doesn't have to be positive integers. You can reorder any set and make it be well ordered, where every non-empty subset has a least element. Not the standard ordering. So, for example, the real numbers under the standard ordering doesn't have a least element. There's all sorts of things that you can show, but for example, there's not a least element that's in that set. You can get as close as you'd ever want to 0, but never hit it, right? So in order to get a well ordering of the real numbers, you'd have to do a different ordering. It is equivalent to something that's referred to as the axiom of choice to be able to do that. The axiom of choice basically says you can make infinitely many simultaneous choices. That's what the axiom of choice says. So, for example, if you had a relation, so remember, a relation means that I have inputs and outputs, but I don't necessarily get a unique output for every input. That's a function, right? What the axiom of choice is that if I have any relation, even if I have an infinite domain, I can make a function out of it. That's what it's referred to as a choice function. Say 1 gets mapped to 3 and 7. Well, I can use the 3. And then if the 2 gets mapped to 5 and 9, I can use the 9, and so on down the line. That's what the axiom of choice gives you. Turns out that well-ordering principle for any set is equivalent to the axiom of choice. So you can't actually prove that it's a theorem. You have to accept it as an axiom. Like I said, you don't need to know that. Math gets weird. I know. That's why I like it. Okay. All right. You want to see something weird? There is a paradox that says that you can take a sphere and cut it into 4 parts and put it back together and get double the volume. That's the Banach-Tarski theorem. You can't actually physically do it, but you can mathematically do it. That you can cut it into 4 pieces. As a matter of fact, one of the pieces is a single point. Take it, rearrange it, and put it back together again. It's a weird thing. It's fun stuff. Banach-Tarski, if you want to look it up. Has nothing to do with abstract algebra.
It's not spelled like that.
There, there's actually a video where these people are just going over and over again saying Bonner-Tarski, and an orange becomes 2, and then 2 oranges become 4. It's amusing. Anyway, like I said, it has nothing to do with what we're doing. All right, so as a practice problem that I want you to do out of this particular section, I want you to look at number 9 on page 9. It's very similar to what we just did. Important part from this particular section that I want you to know is the statement of the division algorithm, how we write something was a quotient and remainder. We will use that later on. All right, so let's jump ahead to the next section. So we just talked about that. We can have, no matter what integers we talk about, we can have a quotient and a remainder. Now, when we talk about quotients and remainders, we typically think of integers or maybe polynomials when we divide, but not every instance when we divide are we going to have quotients and remainders. A lot of times what we're interested in dividing is whether or not something actually goes into the number or goes into the element. So that's when we're going to talk about our divisibility. We're going to state these in terms of integers, but these statements about divisibility can be extended to different types of multiplication, depending on what the structure is. Okay. But we'll state it in terms of integers to start with. So let's let A and B be integers again. That's interesting. That's I'm going to change up what the definition is in here. The definition in your text says B is not equal to 0. That's doesn't have to be, B could be 0 in this case. It's just it wouldn't be unique in that case. So I'm going to eliminate that particular condition. We say that lots of different words. B divides A. Or B is a divisor of A. B is a factor of A. Or A is a multiple of B. All those mean exactly the same thing. B divides A, B is a divisor of A, B is a factor of A is a multiple of B. Those literally all mean the exact same thing. If, all right, what does it mean for B to divide A? Well, we're thinking about things being in the integers in general. Pardon me. They may not necessarily be integers, but in general, for integers, we don't like to write things as fractions. So I like to think about that last statement. A is a multiple of B, which gives me what the definition is. Okay. So this is if there exists an integer C such that A is equal to B times C. I know the book definition said B is not equal to 0, but notice that I could make B be 0. What would be the only thing that, using this definition, if B is 0, what's the only possible thing that B could divide? 0, right? Because if I take 0 times the C, I get 0, right? So the only possible thing that 0 could divide is 0. The issue with dividing by 0, of course, is that the answer is not unique, right? 0 times 1 is 0, 0 times 0 is 0, 0 times 8 is 0, 0 times negative 75 is 0, right? It's not that you can't divide by 0. Division by 0 actually is not that big of a deal. The problem is that I don't get a unique answer. That's what we say we can't divide by 0. Okay. In fact, you kind of divide by 0 when you think about doing asymptotes analysis in calculus, right? I'm dividing, if I have a number on top that's not 0, and I have a number on bottom that gets really, really small, we say that gets really, really big. Right? So we are kind of dividing by 0. We're talking about behavior at that point. Right? So it's not that we can't divide by 0. We can absolutely divide by 0. It's just as messy. So that's why I went ahead and eliminated it. So we can actually, but again, in the integers, the way the definition works, the only number that I can divide by 0 is 0. I just don't get a unique answer. Anything else I can't. The 0 doesn't divide into it. However, notice that 0 is divisible by anything, even if it's not 0, right? Because I can just use my C as 0 and get the division that I need. Okay. All right. So just as an example there, oh, I guess I should say notation first, because we like notation. Mathematicians are lazy. We like our notation. Okay. In this case, we would write B and then a vertical bar and then A. So for B divides A, so you get a vertical bar there. What do you think we would write if B doesn't divide A? Yep, put a line through it. Good. Yep. So just like if you do not an element of or not equal to, does not divide is just a line through it. Okay. So far so good? All right. So just as some examples, just to show how the definition works and how you might start to prove things as far as divisibility goes. Certainly, one, I know it gets a little messy because if 1 divides A, it looks like I wrote R bar A. Okay. So that's 1 divides A. So either make your 1 smaller than your bar or, put some little marks on your 1 to illustrate that really is a 1. So 1 divides A no matter what. And why is that? Well, according to the definition, I need 1 times something equals A. What are you going to use for the something? A, yeah. Good. Yep. That's according to the definition, that's why. Okay. Or I just mentioned this a minute ago. B divides 0 no matter what B divides, because B times what always gives you 0. 0, yeah. So 1 divides anything, anything divides 0. Including 0. There's nothing wrong with 0 dividing 0. Even though the book says don't worry about it yet.
Well, yeah, 0 divided by 0 is 1.
Yeah. Is it 1 or it's also pi?
Sure.
Yeah. Negative q root of 7. It's all those things. All right. So anyway. So, they mentioned a few things that make sense if you think about them. So, for example, if we have B divides A, then we know that our A is B times C. But if I think about kind of multiplying both sides by a -1, if you will, I want to write it a little bit differently. If I think about doing the opposite of both sides, multiply both sides by -1. Notice that if I have B divides A, then I also get this negative A is B times negative C, which tells me that B also divides negative A. So if B divides A, it divides its opposite, and vice versa. It would work the other way. So what this tells us is that the set of divisors for A is also the same as the set of divisors for negative A. So hence, A and negative A have the same set of divisors. Now this is something that's going to be a bigger concept later, but notice that in the integers, what are the only two numbers in the integers that you can divide every other integer by and still get an integer? There are exactly two of them in the integers. So there's two integers in which you can divide absolutely every other integer and get an integer every single time. What are those two numbers? One and negative one, right? So notice that coefficient out in front of the a there will be 1. The one out in front of the negative a would be a negative 1. I can divide everything by 1 and negative 1. We refer to those kind of numbers, I can always divide by those. We refer to those as units. So the integers only have 2 units. We'll talk about more about units later. Okay. Units are the things that we can always divide by. I can sometimes divide by 2 in the integers, but I can't always divide by 2, right? So that's why 2 is not a unit. But I can always divide by 1. I can always divide by negative 1. So the units are the things that you can always divide by no matter what. Right. When it comes to doing factorization, and you've talked about prime factorization before in your life. Remember you had 2, 3, 5, those are primes, right? But did you ever talk about negative 2, negative 3, negative 5 being primes? No, they are. They are primes. The issue is that I've taken a prime, it's not an issue. I've taken a prime, I've multiplied it by a unit. The unit doesn't do me any good because I can always divide it out. Okay. That's why you never worry about doing prime factors and saying, well, negative 2 is a prime and negative 7 is a prime, because I can always just divide out the unit no matter what. Okay. So when you worry about prime factorizations, you don't worry about units in the factorizations. Okay. It's also why 1's not a prime. In particular, if 1 were a prime, you wouldn't get unique factorization because 1 is the same thing as 1 times 1 is the same thing as 1 times 1 times 1. I have multiple factorizations. So anyway, the idea behind the reason why I wanted to mention that is because if you have units, you tend to ignore them in the factorizations. Okay. Because I can always divide them out. Anyway, so we know that the positives and the negatives have the same set of divisors, so that's not any big deal. Which would also mean that they would have the same set of positive divisors, and so when we get there, they would have the same set of prime divisors. All right. Pardon me. Sorry. So let's look at another remark that they have in here. They also talk about if we also have this A is equal to B times C, I can do the absolute value of everything. And absolute value will break up over products. So we would have absolute value of A is equal to absolute value of B times absolute value of C. So this would tell us that the absolute value of B would divide absolute value of A, which is not a huge surprise. Okay. But it also tells you something else, that which of those two numbers of absolute value of A and absolute value of B, which one would be the bigger, or would be definitely greater than or equal to the other? Which one's likely to be the bigger one? Yeah, the absolute value of A, right? Okay. I can't say that if they're negatives, of course, because I can have a bigger negative number, right? A number with more negatives. That's why we look at the absolute values. But certainly, the idea behind this is that, at least in terms of size, in terms of absolute value, the divisor is smaller than the thing you're dividing into, which makes sense, right? So this would tell us that your absolute value of B is less than or equal to your absolute value of A. And we could rewrite this statement in terms of just B, if absolute value of B is less than the absolute value of A, then B is not any bigger than the absolute value of A, but it's also not any less than the opposite of the absolute value of A. So this tells us a couple of things. One, every divisor can only get so big, right? You can't get any divisor of A, can't get any bigger than the absolute value of A. But the other thing it also tells us is they can't get too small. So can we have infinitely many integer divisors of a number, of another integer? No. So there's only a finite number of slots that B can take up, right? Again, if we think of a number line idea, you've got negative absolute value of A, absolute value of A, and I can only hit the dashes, right? I can't go in between. There's a finite number of dashes that we can put for divisors, right? So again, this statement says, well, first, every divisor of A is less than or equal to absolute value of A, and two, there are finitely many divisors of A. Not huge earth-shattering results by any stretch of the imagination, but important. Okay. So let's see if we can do, let's see if I've got one picked out for division stuff here. Okay. Let's look at, this is number 4B on page 14. And some of these look like proofs that we didn't discrete. Well, 5 of you did discrete. 4? You haven't done discrete either?
I'm in discrete.
Oh, 4 of you. I'm sorry. I've been picking on Jenna. I should be picking on both of you. All right. So let's look. This is 4B. So this says that if A divides B and A divides C, then A divides BR plus CT. I don't know why they use R and C or R and T for any R and T in Z. I don't know why they didn't use R and S or S and T or X and Y. So let me skip the letter. That's fine. Doesn't matter. All right. All of you have had linear. All of you had me for linear. Yes, okay. When I take two things and I multiply them by constants and then add them together, what kind of a thing do we make in linear? They have the word linear in it.
Linear transformation.
Close. Combination, linear combination. So what this says is that if I have a common divisor of of B and C, then it divides any linear combination of B and C, is what this says. Okay. So let's think about how we need to prove something like this. Okay. So what I would do, we don't have a lot of machinery. We haven't built up a lot of machinery yet, right? We have the definition of divisibility. That's basically it. Okay. So the way I would attack this type of problem would be, I would use my definition to write this statement. Okay. And then also use the definition so that I see this statement. Okay. Start with the definition for divisibility, rearrange some things, and see if I see the definition of divisibility again, is the idea. Okay. So as far as a proof goes, I'm going to suppose, because I don't want to suppose, I'm going to suppose, all right? Let's suppose that A divides B and A divides C. If you want another shorthand for suppose, by the way, some people will write an S and then make a P. Yeah.
I kind of like that. I'm going to do that.
All right. So again, thinking of definition of divisibility, how can we rewrite what these symbols mean?
A is equal to BR, and A is equal to CT.
Okay, so probably don't want to use the R and the T because that's what I want to do at the end is multiply by them. But you're exactly right. Same idea. So A is equal to B times, just pick a different letter. I'll call it X. And A is equal to C times Y for some X and Y in the integers. I didn't want to use the R and the T because I didn't want to multiply by the R and the T. Oops. Yes, switched. Yep, thanks. Yep. Oops. Yep, they flipped it around because instead of having B dividing A, they made A divide B. Yep, exactly right. We would have realized that here in a second. All right, so now we want to get to A divides BR plus CT. So again, thinking about the definition of divisibility, what do we need? If I want A divides BR plus CT, what do we need to see in terms of the definition? So you told me that over here we had A times something equals B, right? A times something equals C because A divided B and A divided C. So if I want to go the other way, if I want to know that A divides this, what do we need to see at the end?
BR plus CT is a combination of.
Which is A times something.
Yeah, this is A times something, right? The BR plus CT is A times something, right? So if I want to see BR and CT, what do you think I should do with these equations?
Substitute them.
Substitute them where?
Like the AX times the R and the AY times T.
Okay, so I don't know this yet. I need to create this, right? So rather than substituting, I probably want to do what? I know these equations exist. I gotta do something before I add them. I need to see a BR and a CT.
Oh, multiply them by R and T.
Yeah, we need to multiply by R and T and then add them together, right? So now, what's BR equal to? Okay, A, and I'll write it as XR this way. And CT would be AYT. And what does that give us? Oops. What do we want to do with those two equations now? Add them. So BR plus CT will be A times XR plus A times YT. What can you do on the right-hand side? Factor out an A. Now do we have A times something gives us BR plus CT? Now the only thing we need to worry about, and it's not a big worry, but the only thing we need to worry about is that the A times something gives me that. This something is the right type of something. Everything right now has to be integers, is what we're talking about, right? Is XR plus YT an integer? Yeah, okay. So since I'll write them in alphabetical order perhaps. Since the R, the T, the X, and the Y are all integers, we have that XR plus YT is an integer, hence A divides BR plus CT. Good news is that when you do get farther along in discrete this semester, you'll probably be doing these exact same proofs again. These are pretty standard proofs in discrete. So you're welcome. All right, so the process makes sense. This is a pretty helpful result, by the way. If I know that I divide the pieces, I divide the whole sum. Basically what this says. So this turns out to be pretty helpful in different proofs later on. So far, so good? Okay. All right, so now that we've talked about some divisor things, one of the things we can start talking about are common divisors. So notice in this case that A would be a common divisor of B and C the way it's written. And since we know we have a finite number of divisors for different integers, we can take the list of things that divides B, take the list of the things that divide C, see what they have in common, and then which one's the biggest. Okay. So we can refer to that as a greatest common divisor, right? So, as a definition, let's let A and B be integers. And in this case, I really do need where at least one of them is not 0. Remember, anything divides 0. So if they're both 0, then I'm not going to get a greatest common divisor because I have infinitely many divisors for that 0. Okay. All right. So, then the greatest common divisor of A and B, usually we say GCD, just for short, right? Use the acronym. We also use a notation that you're probably not going to like very much because it can get confusing later on. Okay. I'll write it down in a minute. Okay. The greatest common divisor of A and B is the largest of all the common divisors. Of A and B, or in other words, D is the GCD. I'm just going to go ahead and use the notation. It looks like an ordered pair. That's why I said it kind of look like particularly like the notation. GCD of A and B. If you just see an ordered pair and you're not talking about an actual ordered pair, it means the GCD of the two numbers. Later on, we'll talk about ordered pairs and we mean ordered pair. So that's why I said you're not going to like it very much. I don't like it very much. If you want to make sure that you know you're talking about GCD, feel free to write GCD in front of it. Okay, that's not a problem. Right. So D is the GCD of A and B if it satisfies two conditions. The first one is, well, if it's going to be a GCD, it better be a CD. It better be a common divisor of A and B, right? Okay. It also needs to be the biggest among all common divisors. So if we have another common divisor of A and B, then it must also be, it can't be any bigger. So if C divides A and C divides B, then C must be less than or equal to D. It's the biggest among all the common divisors. As long as not both of your numbers are 0, the greatest common divisor of the two will always exist without any issues. Okay? No problems at all with that. All right, so let's see if we can do a couple of examples with this. Not with numbers, because there's different ways that you can find the GCDs of the numbers. I'm more interested in properties here in a little bit. So this is number 11. Number 11, part A, says, what are the possible values of the GCD of n and n plus 2? And this also uses that previous result we proved about. If you divide two pieces, it divides the linear combination. That's how we're going to get at what the possible values are. But let's just think about it. If you have no idea, you might want to just start plugging in some numbers, right? Plug in some different values for n. Well, if I plug in 1 for n, what numbers do you get? 1 and 3. GCD of 1 and 3 is 1. Plug in 2 for n now. What do you get? 2 and 4. GCD is 2. Plug in 3, you get 3 and 5, and the GCD is 1. Plug in 4, you get 4 and 6. The GCD is 2, right? So what do you think the possible values are? 1 and 2. Hey, that's a big surprise. But let's see why. Okay. I said that we can probably get at this by using the idea that if I have a common divisor of two things, and it also has to divide any linear combination. Now, linear combinations can work adding, but they can also work subtracting. Nothing says that I can't multiply by a negative, right? Can I get a linear combination of n and n plus 2 that gives me a pretty small number, relatively speaking? Can I combine n and n plus 2 and get something relatively small? Not too tricky. How can I combine n and n plus 2 and get rid of the n? Well, I'm not thinking about plugging something in for n. I want to combine, no matter what the n is, how can I combine the n and the n plus 2 and get rid of the n? Yeah, or the other way around, right? Yeah, so I do the n plus 2 minus n. So if I do n plus 2 minus n, I get 2, right? So now again, GCD is greatest common divisor, but let's think about it just in terms of common divisors. If something divides n plus 2 and something divides n, what else is it going to have to divide? If it divides this piece and this piece,
We have to divide their sum.
yeah, it has to divide their sum or their difference. It has to divide the 2, right? So if it divides the n plus 2 and it divides the n, it has to divide 2. So what are your choices for common divisors? 1 and 2, which is exactly what we were seeing by plugging in different values, right? So the possible values for this are 1 and 2. That's all you can possibly get. So part B says, what are the possible values? If I can write. Of the GCD of n and n plus 6.
I had to guess.
Yeah.
1 or 6.
And so I agree with the 1 and the 6, all right? Okay, 1, 2, 3. If we use the same argument that we had here, we know that we'd had to, if it divides this and divides this, then it's going to have to divide that, right? Well, so it had to be the divisors of 6, correct? It's going to have to divide the 6. So 1, 2, 3, and 6. It might be. Yeah, exactly right. And it's the same exact argument, right? N plus 6 minus n is going to give you 6. So if you have something that divides both n and n plus 6, it has to divide the 6. The divisors of 6 are 1, 2, 3, and 6. So that's it. That okay? Okay. All right. So one other important concept for the GCD is the idea that we can write the GCD as a linear combination. So this is a theorem. Let's let A and B be integers. Again, not both 0. And let's I'll call it D, be the GCD of A and B. Then there exist X and Y in Z such that D is equal to AX plus BY. You can always write the GCD of two integers as a linear combination of the two integers. It's kind of a cool property. It's also a consequence of the well-ordering principle. Notice this is not unique, by the way. For example, you just told me a second ago that the GCD of 3 and 5 is 1. One way to write this would be 2 times 3 plus 5 times negative 1, right? But I could also do, I guess I could read it the other way, 2 times 5 plus 3 times negative 3, right? They don't, the X and the Y don't have to be unique. All we're saying is that they exist. There's no uniqueness here. You can say, however, certainly the GCD can't be any bigger than A and B. So they can't both be positive if A and B are both positive, for example, right? If A and B are both positive, one's going to have to be positive and one's going to have to be negative to get the math to work out. Right. Again, the idea, I'm not going to go through the proof because we've got about 3 minutes. But I'll tell you again the idea of how we would do this is that you would let your S be the set of all possible linear combinations of A and B that are positive. Again, you need to make sure you have a non-empty set, right? Before you can apply the well-ordering principle, it has to be a non-empty subset of the positive integers. Okay? As long as they're not both 0, even if they're negative, as long as they're not both 0, you can make positive numbers pretty easily. A and B are integers, so use A is equal to R and B is equal to, or excuse me, R is equal to A and S is equal to B. And you'll get A squared plus B squared, which is certainly not negative. Right? So I can make that a non-empty subset, right? So S is not the empty set since A squared plus B squared is in S. Then the proof goes that the smallest element of this set, this is a well-ordering principle. Like I said, I'm going to stop since I got about 1 minute. The smallest element here exists. Well-ordering principle says that that is the smallest element. So you would need to show that it is a common divisor of A and B, and then show that it's the greatest of all common divisors. Okay. The idea, though, to show that it's the greatest is just the idea that we talked about. If I know that I can write something as a linear combination, if something divides A and something divides B, then it divides the linear combination, so it'll divide that element, right? So remember when we say greatest common divisor, we said that if C divided A and C divided B, it had to be less than or equal to D. We actually know that it actually has to divide D by this result. So I'll finish this up next time. Let me give you one more problem to work on. I think I had one more problem. Yep, I'll give you one more problem next time. They all involve greatest common divisor, and I want to do another example of that. So never mind. Just do the one problem that I gave somewhere in there. List of things. All right. Is this okay in here?
Yep.
Yep. We happy in here?
I like it.
Yep. Yeah. That was it. Page 9. Yep. Page 9, number 9. Yep. All right. I'll see you Thursday, if not before.